In this video, we are going to review the calculation section of the determining specific heat of a metal lab. Before we get into the calculations, I just want to remind you that in the data and observations section, data and observations is the heading of that section. You want to make sure to include the unknown metal number, so whatever your sample number was, as well as some qualitative observations. What did the metal look like? And then you will include the data table. So the data table is part of the data and observations section, but every data table needs to have a number and a title. So for example, this might be data table 1, masses and temperatures. You could title it whatever. Then we can move on to the calculations section. So calculations is the next section in your lab notebook. And for your calculations, remember you always need to label the calculation and show at least one sample calculation. And in your lab notebook, it will also be useful if you box your answers. So what we're going to do is we're going to go ahead and just look at what our calculations would look like in our lab notebook. So I'll go ahead and label it calculations. And then I'm just going to go through the calculations just like they are in the lab handout. So calculation 1 says calculate the mass of water. So I'll just label it mass of H2O. And then I will use the data in my data table. Now your data will probably be different. Might be the same, might be different. But we're going to use the data in the data table, not in the pre-lab, but in the data table to calculate the mass of water. So we have mass of water and calorimeter, and the mass of just the calorimeter. And so what we can do is we can just subtract those. So I will say mass of water in calorimeter is 77.5 grams minus the empty calorimeter is 4.40 grams. And then I can plug that into my calculator, get an answer. Make sure you box your answer. So the second calculation says calculate the temperature change for the metal and for the water. So you only need to show the temperature change calculation one time, then you can just write the answer for your other one. So I'll go ahead and just label this temperature changes. And I'll show a calculation for one of them. So I will show it for the metal. Delta T of the metal is T final minus T initial. Remember that delta T could be positive or negative. And so what I'm going to do is I'm going to take my data. So the maximum temperature of the metal and water in the calorimeter, that was the temperature at the very end. So you're going to take your maximum temperature at the end, and you're going to subtract the temperature of the hot water bath, because the temperature of the hot water bath we are assuming is the same as the temperature of the metal. So for my sample data, it would be 24.3 degrees Celsius minus 99 degrees Celsius. I'm going to have some negative temperature. Then I can go ahead and just write the answer for delta T of water. You can show the work if you want, but you don't have to. This should be a positive value. The water warmed up. Metal cooled down, water warmed up. So calculation 3. Calculation 3 says calculate the heat gained by the water in the calorimeter. We're going to label it QW. So I'll label this calculation heat absorbed by H2O. And now I'm going to be using Q. So when I'm solving for heat, this is like what you did in the pre-lab. In the background information, they gave us the equation, Q equals mc delta T. So if I'm solving for Q of water, that means I need the mass of water, the specific heat of water, and the change in temperature of water. So we need to look at our data table and find the mass of water. The specific heat of water was given in the background information, and delta T of water we just calculated up here. So plug all of your values in, and your answer will be in joules. Should be a positive value. Again, C is joules per gram degree Celsius. It's in the background information for the value of C. That gives you your Q of water. Number 4, assuming the heat gained by water was lost by the metal. So the heat gained by the water, the heat that the water absorbed, was lost by the metal. First law of thermodynamics says that energy is neither created nor destroyed. So the energy that was absorbed by the water had to be lost by the metal. So this says what simple relation holds for QW and QM. So for 4, I'll just label it first law of thermo. I still need to label all my calculations. First law of thermodynamics says the heat absorbed by water is equal but opposite in sign to the heat lost by the metal. So whatever your value is in number 3, if we put a negative in front of it, that's the heat that was released by the metal. So the number 5 says rearrange the heat equation. Heat equation is MC delta T. And solve for the value of C, the specific heat of the metal. So I'll label my calculation specific heat of metal. So the heat equation is Q equals MC delta T. So if I want to rearrange this for specific heat of the metal, I'll divide M and delta T over. It's going to be Q of the metal over the mass of the metal times the delta T of the metal. Notice how I put this quantity in parentheses on the bottom. So it's Q divided by mass times delta T. Be careful with your order of operations there. So we're going to actually plug in our values. Q of the metal, we've already said, is the negative value from number 3. So we're going to have a negative number of joules. You can plug your numbers in. Mass of the metal will come from our data table. So look at your data table. And your delta T, which is degrees Celsius, comes from number 2. Okay, so again, we want Q of the metal, that should be negative. Delta T is also negative, so those negatives will cancel out. C should always be positive. Specific heat is always a positive value. So when I solve, I'm going to get joules per gram degrees Celsius. Those are your units for specific heat. How much energy does it take to heat 1 gram of the metal by 1 degree Celsius? And then number 6 says look up the accepted value of specific heat for your metal and calculate the percent error of your results. So I'll just label this as percent error. So depending on your sample number, samples 1 through 4 and 9 through 12 were lead. Samples 5 through 8 were copper. So depending on if you had lead or copper, you can look up the specific heat of lead or the specific heat of copper, see what that value is. So you can go ahead and the first thing I want you to do is write what the specific heat is over here. Then we're going to calculate percent error. So just a reminder, percent error is the absolute value of experimental value. Experimental is what we just found in the lab, minus the actual value. That's what we wrote down here. Divided by actual times 100. So take what you calculated in 5, subtract what it was supposed to be. Make sure that's a positive number. Percent error is always positive. Take that number, divide by what it's actually supposed to be, and then multiply by 100. So that will give you your percent error. Remember, the lower the percent error, the better. Now, if it's a high percent error, don't worry. When I did this, I got a 97% error for one of the metals. So it's okay if it's high. That's why we look at sources of error. So then you will look at the post-lab questions. So post-lab questions are more conceptual. So you'll go through the post-lab questions. You do not have to rewrite them. Just answer them in your lab notebook. After post-lab questions, if you take a look at the rubric, you'll also be writing a data analysis. So focus on at least 2 sources of error and how the sources of error affected the results. And then you'll go ahead and write a conclusion. Conclusion is purpose. Was it fulfilled? Why or why not? Be specific with the why or why not.